Allison was making the J65. Westinghouse was making the J34. And I don't know, there's a couple others. Oh, Arenda in Canada was making the Navy Row Arenda. I don't remember. Navy Row was making the Arenda engine. I designed an afterburner for that one. I designed an afterburner for every jet engine that was being made in the United States that year. When I designed the first afterburner, they said you can never do this, never work. This thing will never work and never stay together. Until I showed them it would, and then after that, everybody did it. The way an afterburner works is normally a jet engine cannot burn all the air that for the fuel that's going in. It comes in very, very lean because of the fact got to keep the temperature down, because the blades of the turbine have to have a lower temperature, and that's well below the combustion temperature. So they pump in a lot of extra air. So when you come into the afterburner, what you can do is burn up that extra air by adding fuel, and you get extra thrust that way. That's the way an afterburner works. Okay? All right. I designed the first one for the GE J47. I designed the first one for them. And that's exactly the way I designed it. And then they designed this one themselves. You see?
What do they put in?
Nothing. It's made exactly with the actuating rings that I had in it, exactly the way I did it. See that combustor, the gutters?
Yeah.
Those are exactly the ones we designed in 1949. Gotta take a picture of that just to prove that. They haven't changed a thing. They haven't changed it at all. You see the the liner on the inside? I put that liner in there because when it entered into afterburner, it started to screech. And so that was terrible. It would just tear everything apart. So I put that liner in to cool it down, and it stopped the screech too at the same time, which I was very surprised.
I think my refrigerator is making a similar screech now, Dad.
You put a liner in it,
okay.
That'll solve it. But the whole idea of the variable nozzle, the variable shroud on the outside, that's part of my patent too. That's part of the whole patent that I have. This matches up with the outside of the airplane. This is a turbofan engine. See the turbofan? And what they have in this one, because this is half of it's missing out in the front. But what you do is you have another set of blades out there, and you have air going on the outside alongside of the jet itself. So the jet comes out the back end, just as it did before. Here's where the jet comes out. But here you pump extra air along the outside of the jet. See the efficiency, the thrust efficiency of a jet engine, of an airplane, depends upon how close you can match the exhaust coming out of the jet to the flight of the airplane. When you get those two running as close as possible, the velocity of the jet coming out equals the velocity of the airplane, you get the maximum thrust efficiency out of the system. But what happens with a jet engine? Normally a jet engine comes out almost at sonic velocity, and most airplanes are subsonic. You see? Are you with me? So what you do is you take extra air along the outside and you mix it with the sonic velocity of the exhaust to slow it down, and then the exhaust approaches the speed of the airplane, and that gives you the maximum efficiency. And that's why they're all turbofans. You see, they don't do that with a fighter airplane, because the fighter airplanes are running almost sonic velocity. They'll go at that speed, but very few jets run at that speed. That's why you have a turbofan, and they call that a fan that brings it in. And you'll see all the new airplanes, you'll see with a big section out in front. That's the fan blades. You have a slow-speed airplane, you don't even want a jet, you want a propeller, because then the exhaust coming out of the propeller is slow, matches it. And it's roughly 1,000 horsepower machine, but they upped it later to 1,200 horsepower. But this one was in competition to the Rolls-Royce. This was made by Packard Allison, they're called a Rolls-Royce engine. It was used in the Spitfire and also used in the P-51. But we were using this also in the P-51. The Rolls-Royce engine Merlin. It's called a Rolls-Royce Merlin. It was very similar in shape to this one. It had about the same horsepower. Anyway, it's a water-cooled engine for a propeller-driven aircraft, and was used in the P-51, and the Rolls-Royce Merlin was also used in the P-51. First engine in the free-wheel design and built by Frank Whittle. See, quadrant Frank Whittle in England. See, the air comes in here and here, comes in like this. It gets thrown out by this whirling rotary compressor out into these chambers, and then it goes into the combustion chamber. Goes into the combustion chamber and comes back out again. Goes into the inside and reverts back, comes back into the turbine wheel, and then goes out the back end. So this is really a copy of Whittle's engine. And General Electric made the first ones.
I have a question.
You got a question? Hurry, I got somebody ask a question.
Did you design parts on the B-24 bomber?
On the B-24 bomber? No, I didn't work on the
Okay.
B-24 bomber. I'm sorry. That was the B-32. The B-24, they were making the B-24 when we were in technical.
That's what I'm asking you.
No, she said that I worked on it. I didn't work on it.
You didn't work on it?
No, I didn't.
They were
I
making,
worked-
that was what I saw in the,
Right, when you were down on the assembly line.
They have one there?
Down on the assembly line.
oh, they were, huh?
They have one here outside, maybe?
I don't know.
Oh,
We'll
probably.
find out.
Probably.
And what were you?
I was working on the B-32, which was the equivalent of the B-29, which is like the B-17. The next biggest airplane was the B-29, which was, of course, the Enola Gay and everything else. But Convair was building a competitive airplane called the B-32, which is the same size as the B-29. You see, and the B-24 was like the B-17, about the size. The B-29 and the B-32 were about the same size, and I worked on the B-32. Then I worked on the B-36, which was the biggest airplane in the world. I started working on a full-size airplane, and to that time, the only airplane I ever built was a model airplane. On the B-36, I designed the vertical rudder on that. Well, that's no small job. The vertical rudder was almost 10 stories high on that airplane. That's how big it was. So I designed that one and worked on the drawings for that, and then I laid out the whole front cabin with the B-36. I designed the whole front cabin with the flight controls and everything else. I mean, I laid it out. I didn't do the actual detailed design. The air is brought in here. See, in these rotors, they're like centrifugal water pumps. They run around, you see, they rotate around, and they take the air in and they throw it out. And that's how it pumps air, like a water pump does the same thing. Then it goes up into these chambers, up into here, you see, it's collected in these things, comes up into here, it goes out around and comes into the combustion chamber, which you see right here in red. And then the fuel is injected through the nozzle, and the stuff burns, and then the hot gases are ducted down through this turbine wheel. And the turbine wheel then drives the air pump, which is the air compressor section, and then the exhaust gases jet out the back, and the jet is what gives it its thrust. Okay? This type of an engine is a little different. These are called radial flow engines because the airflow goes radially, see? These are axial flow engines because this takes in the air, and then in an axial direction, and by all these little fan blades pumps it up to high pressure so that it'll go through. Okay? So these are axial flow engines, these are radial flow engines. Nobody makes radial flow engines anymore.
Not efficient?
They're not as efficient as an axial flow engine, and also you can make axial flow engines more compact. You know, in an airplane you want to keep the diameter down. As you can see how much smaller in diameter that is compared to this. The next thing they did when they first designed these things was they decided instead of having the external can combustors, they put them inside. So here you see them all on the inside. The compressor section is gone out of this thing here, but it would bring it in directly into here, still having cans for the combustion. Same way, you know, fuel injector, the big can right over there. These are all individual fuel injectors. So that was the next thing they did.
And that's what this is right here opened up.
Yeah, there's one of the cans. They're sort of complicated can combustor, but it's still individual. They call them cans, individual cans. And then later they made an annular. I don't know whether they got one here. They made an annular combustor where, in effect, what they did was they make one great big can like this with an inner liner, and then you have an annular combustion space. It's like connecting all the cans together, see, into one combustor. That's the way all the newer models are made. That's a B-24. That was the one that we were making in Fort Worth when Mother and I got married and went down to Fort Worth. She worked in the office.
Okay.
She was upstairs. I don't know what she was. She worked in the office work. She's typing, and secretarial work and that kind of stuff. Meanwhile, I was working on the B-32 version of this, which was the bigger model of that. And then the B-36.
Convair had a plant there?
Oh yeah, great big plant. It was in Fort Worth. Huge plant. They had a plant in San Diego, which is the plant downtown there, and they were making the B-30. They were making the C-99 here in San Diego, which was the cargo version of the B-36, and they were making it. And when I laid out the front cabin, they sent it to San Diego to be approved because they wanted to make sure the two things would mesh, the two airplanes. And then those people all came to Fort Worth because I was doing the cabin design. They weren't doing it, and they were all upset because they wanted to do the cabin design, and I was doing the cabin design in Fort Worth. So I thought, well, maybe they're going to send me to San Diego, but they didn't. They had all those other guys came out.
Ditto all over my hands every day, that's all. They had this purple ditto.
Yeah, and you
machines.
cranked
Well,
the-
I just typed on the paper.
And
I
take her at
didn't.
lunchtime. I take her down in the shop and show her all the
And
airplanes.
when he didn't, I used to sit in the office and hear the buyers talking, and that's when I wanted to leave because I heard him say open season on the you-know-what, Negroes.
Oh.
And they didn't say it that way. And I went home and I told your dad, well, the Jews are next. They finish the Negroes, they'll come after us. So I said, let's leave.
What do you
I
mean?
couldn't stand it.
What did they mean? Open season? They just gonna?
Just go out and shoot them. That's all.
That's what they were
wanted
doing
to
in
do.
Texas?
No, we're just joking. That's
Oh.
what they wanted to do. They wanted to get open season on them like you do on animals. I mean, they did talk like that, Gerald.
Oh.
The lady next door had that maid working for her and treated her like a queen while she was in her house, working for her. And talked to her, and I said if she'd pass her on the street, she'd knock her off out into the street. She wouldn't, that's the kind of people they were.
They use these turbochargers on these particular machines here. They used them. And they went up to 40,000 feet. In order to have an engine like this operate, you really had to have a turbocharger, which is like you have on cars, except that these were General Electric made these. And you bring in the exhaust gases driving this turbine wheel on out, and it drives a blower, a compressor down through here that pumps it into the carburetor on the top, right down through here. Brings the high pressure air. And what that does is it pumps more air through the engine. The horsepower of an engine depends upon the mass flow, how much airflow you can get through it. If you can pump more air through it, you get more power out of it. You see, and so as you go up in altitude, up to 30 or 40,000 feet, the air gets very thin, and so the mass flow, even though the volumetric flow is the same, the mass flow is way down. So what you have to do, if you really want to maintain your power at high altitude, is to pump more air, compress more air before it goes into the engine. And that's what this does. And this way you use the exhaust gases to drive a compressor or a pump to pump more air into it. And that's what they have on cars too. They have these things. There's also a supercharger that they're putting on cars. In a supercharger, you don't have a little turbine driving the pump. It's connected directly to the shaft by a belt. And the belt drives the pump, which pumps air, or the blower that pumps air into the engine. and they call those superchargers. So whenever you see the ads, it's a supercharger engine. You'll know it doesn't have a turbine driving the blower. Okay. If it says it's turbocharged, you know it's got a little turbine driving.
Very good.
Okay. So both of them.
Not just stand still in one spot and talk the morning away.
You see those little green bubbles? Mm-hmm. Just back of that front cabin, the wall was right back of that, and so everything forward of that line, I laid out that whole section, including the greenhouse up at the top, those little bubbles you see on the flight deck, the whole works. Laid out that whole front cabin, and there's the rudder that I worked on first when I first got out of college. The first thing I was assigned to work on was that rudder.
Did it
They
move?
asked- Oh, sure, it moved.
Where's the rudder?
You can't see it.
Oh,
It's
it's
part of this.
It's on the back.
Yeah, part was in there. So first they had me design a rib, one rib in the horizontal stabilizer. And after he saw what I did on that, he says, well, I'm going to give you the rudder. You better lay out the rudder. And I said, what does that mean? You know, here I'm just fresh out of college. I'm 23 years old. I don't know from nothing, you know, and he's telling me I got to design the rudder for that thing. It was pretty interesting, though. See, this airplane went supersonic, and because it has supersonic, the shock wave that forms at the nose, if they didn't have this spike out in front, the shock wave when you go supersonic, there's something called a shock wave that forms. A shock wave is a compressibility wave, and it acts like an actual dam. It doesn't let stuff through it. And so the shock wave would form right at the edge of the inlet and wouldn't let any air in. And so what they have to do is they put this spike out in front, so the shock wave forms at the tip and goes up like this, see, and never comes near there. Once it goes through the shock wave, the air is no longer supersonic, it is subsonic, and it'll go into the inlet very smoothly in the inlet and flow. But the thing is that as you vary the speed, the shock wave changes. So this spike is made so that it can move in and out. And they adjust this spike, depending on the speed that they're going, how fast they're going. Like if they go just supersonic, or maybe they go twice the speed of sound, or 3 times the speed of sound, or 4 spine, there's a different place for that spike to keep that shock wave from entering into the inlet. See, it gets very complicated to make those things work. Then when it's on the ground, they want to suck in, because this is designed for high-speed flight. There can't be enough air coming into this thing when it's just sitting on the ground and they're taking off. So they bring in air through these vents up at the top. You see those vents? They bring in, allow it to suck in more air because they can't get enough air. That is not big enough for the air they need to take off on. This is one great machine.
You like that one?
I like that machine.
What's it called?
I like it. It's called the Black Hawk. That's our Black Hawk.
Oh, Black Hawk.
Dad, you want to say anything about this rib that goes here?
Well, this whole thing, because it's a supersonic airplane, the way it was designed, it gets part of its lift at slow speeds. The trouble is, at very slow speeds, when it's taking off, it doesn't really have enough lift to get off. You know, it's designed to go at supersonic, because they haven't changed the wings or anything like that. So the body becomes part of the wing. That's why it's shaped like this. It actually gives part of the lift, and the way it's designed with that very sharp edge, it doesn't detract from the speed too much. It doesn't offer too much drag under supersonic conditions. It was very difficult to design. That's why it's so damn long. They brought it way out in front like this to give extra lift to it. But they have trouble with these because of leakage of fuel, the tanks. In order to design this thing, this does not have these bladder tanks in it. The whole wing section, since everything
this one
was
too? I thought it was just on those fighters that they had the trouble with them.
No, on this one they had a lot of trouble with it.
What is that? What happens?
Well, the joints. I mean, they can't keep the joints sealed up, because now the fuel is really every place they got room to put fuel in it.
Yeah.
So it's like solid fuel all in the back of these sections in here and so it leaks on an ordinary, and most airplanes, they have a rubber bladder on the inside. In fact, fighter airplanes, they always use the bladders anyhow. They very rarely use integral fuel tanks.
What's amazing?
It's amazing that you could make an aluminum structure that would come into something such so huge like this and still stay together. You know, these are all, look how big and massive all this stuff is. And yet that means that there's big forces involved. Of course there is when it lands, you know, huge forces. And yet it's all taken out in this thin stuff. It ends up in supporting it in all this thin aluminum. And of course the structure itself is a monocoque structure, which means that it also absorbs the load. So it all has to be designed, very carefully designed and calculated to make sure it'll handle those loads. These airplanes are still in service.
Oh, I know.
And what they're doing now is there's a big question in Congress. They're trying to get money to refurbish these, and what they want to do, see, this has 8 engines on it, 2 in each pod. There's 4 pods with 8 engines. And what they want to do is, one of the options is to take off these pods and put in a newer engine, you know, a new fan engine, turbofan engine. In which case they'd only have 4 engines instead of 8, because this takes an awful lot of maintenance, because you got 8 engines to take care of on this thing. It's because most of the airframes have like 8,000 or 9,000 hours on them. They're like, there's no wear on the airframes. They're like brand new on all these, so they don't fly very much. So they're thinking of trying to save them by redoing the power plants, redoing the electronics, and so on, rather than try to build, because they don't have anything to replace them. The B-2s won't replace these type of things, and the B-1s, they decided they didn't want to make any more of those, so the only thing left are these B-52s. Look at the shear panels on the sides. You can see the waves. It takes up the load. And it takes up the load, and it actually is designed so that it wrinkles to take up the load. Structure is usually stronger than it needs to be, just so you don't see any of this stuff happening while it's flying along.
Because it will actually, it actually moves around.
You actually
wrinkles.
see it moving as the wings would flap. You know, you see these moving. Well, that's what was absorbing the load. So they didn't like that. So on civil aircraft, you don't see the wings, you don't see the things wrinkling anymore. When it comes in for a landing, or at slow speeds, the wing is straight out. Right. And then when it goes supersonic and high speed, they pull the wing back. Right. So it makes like a big delta out of it. And that's the B-1 bomber does that, the F-111 does that, and the F-14. F-111 F-14 are supposed to be the same. The F-14 is the Navy version. Right. Yeah. And the F-111 is the Air Force version. It takes off, the wings actually go up.
The air?
Yeah, it goes up almost 6 foot, they said. From 3 foot down to 3 foot up. It goes up like that. It flies with it up like that. But when it lands on the ground, it's down like that. The fighter pilot or whoever it is flies down below him, comes in alongside. When he's in the proper place, then the guy, the tanker sergeant, he lowers this thing down, and then he can fly it up and down until
I got you.
2 are together. You know, it's sort of a tricky operation. That was a tanker taking off. Looks out this window here, and he has his controls for controlling the jet, controlling that boom. There are other kinds that sit on the outside of the wing, and it's got a big flexible pipe, you know, a hose that comes down, and that's the drogue. Israel makes a lot of those. They make them, and they outfit them for all the foreign countries. It's called a Boeing Stratocruiser, and it used to fly from New York to London. That's the one I took first flight when I went to London. That's what flew one in one of those. It had berths in it. So we flew over he wanted to have, Bob Day said, we want to have a berth. So at that time, Solar was still allowing us to fly first class. So we actually had a berth. Imagine that. We each had a berth.
Did you get any sleep?
Yeah. We slept in it. I changed clothes and put on my pajamas and slept in it. And I guess so. I can't believe it was that long a flight that we'd have to sleep in. Wasp Majors, a 4300, that has the 28-cylinder engines. You know what I was showing you on the inside? The 4 banks is 7. 28-cylinder engine, that's what that is. We had to design a system that would use a heating system with a ground support cart that had one of the little solar gas turbines driving it, and it would have these ducts that would plug into this to pump heated air into the airplane and also through the engines. This was so they could be standby in the north where the temperatures were down to 65 degrees below zero, and they would be ready to roll, so they had to keep everything warm. So anyway, we designed this APU, this power unit, ground support unit, that would supply hot air to the engines to keep the engine warm and also to the air conditioning system. So on this, we had to plug into that thing. This is the old building at Solar up on the 2nd floor. I said, the reason we want to do this is because, you know, if it were aluminum, it would bend, they would bend it up, and it would never fit in there. This way, it's nice and rigid, and nobody can harm it. I said, you could actually throw it out of the window here, and it land on the ground, and it would not hurt it. He says, "You're sure of that?" I says, "Yeah." He grabs the damn thing and throws it out the window. So we ran downstairs. I said, God Almighty, you know, the only one we had, you know, the only model we had of this thing. Run down there and get it. And I watched it. He went out the window and it was bouncing around down on the concrete. You know, we went down to get it, and it was just a couple of edges were banged on it, and that was about it. Everything was fine. He said, "I guess you're right, Ralph. That's pretty good." But every time something would new come in that they wanted me to look at and work on, he said, "You going to design this one out of plastic?"
Well, you throw it out the window.
The efficiency of a wing is the ratio of the drag to the lift. You know, the whole thing you want to keep up. You want to get maximum lift with the least drag. Okay? And the way you get that is by increasing the aspect ratio. The aspect ratio is the ratio of the length of the wing to the chord, the cross chord. So the higher the aspect ratio, that means the longer the wing and the narrower the chord. And the higher aspect ratio is a function, the efficiency of it in flight is a function of speed. At slow speeds, you want the highest aspect ratio. So if you've got an airplane that's going to fly at low speeds and you want it to be efficient, you put long, narrow wings on it. And so the U-2 was a reconnaissance airplane. They used to fly at very high altitudes, but it had to be highly efficient because they wanted to carry as least amount of fuel, and so they put big long wings on it for that. And you can see these also if you ever watch sailplanes, gliders, sailplanes. You notice how long and slender those wings are? That's because of the fact that they go at a very, very slow speed, and so they want highly efficient. They want least drag with maximum lift. And that's one of the problems that occurred. You know these airplanes that crashed back east because of ice forming on the wing? Those airplanes designed over in England were designed with high aspect ratio wings because they are for short hops and they fly at very low speed, so they wanted maximum efficiency. So they made those wings. If you look at that airplane, you'll see that the wings are very long and narrow. Well, that was all right, but whenever you have icing conditions, what happens is the ice builds up and disrupts the airflow. Well, if you get a big wide wing, it doesn't make a heck of a lot of difference if you get some ice. You know, it doesn't bother. But if you get a narrow wing, you know, the ice building up on that narrow blade will disrupt that airflow, and it'll cause that thing, it'll lose all its lift. And that's what happened with those airplanes, and they didn't have proper anti-icing. When the afterburner lights off, it's a very, very horrendous vibration machine, and it just wants to tear everything apart. And so I had designed everything that went on with afterburner. I designed so it was all shock mounted, so that it could absorb all these heavy vibrations. And nobody was doing that. See, nobody knew what to do about it until I did it. And that's why they said it'll never work, but they didn't have anything else. And they needed this device, and they didn't have anything else. So finally they said, well, okay, build it. Go ahead, we'll give you a contract to design it and test it. And we designed it and tested it, and it worked from the first day. So after that, then everybody wanted one, and that's why I say for a while there, I was working day and night designing for every jet engine being manufactured in the United States. I was designing one for them.